August 25th, 2012, something changed at the very edge of our solar system. Voyager 1 was 121 astronomical units from the Sun, nearly 18 billion kilometers away, far beyond Pluto, far beyond anything humans had ever reached before. And in the span of just a few days, three things happened. The solar wind, the steady stream of charged particles flowing outward from the Sun, suddenly collapsed. Galactic cosmic rays surged to levels never measured before, and the surrounding plasma density increased sharply. Three signals, all pointing to the same conclusion. Voyager had crossed into interstellar space. But there was a problem. The magnetic field didn't turn. According to every major model, the boundary between the Sun's influence and the galaxy beyond should have come with a noticeable shift in magnetic direction. A clean rotation, a clear line in the data. It never happened. For nearly a year, scientists argued, had Voyager truly left the solar system? Or was it trapped in something more complicated? Tonight, we retrace that journey to understand not just where the solar system ends, but what Voyager really found. Voyager 1 and Voyager 2 launched in 1977. They were never meant to be interstellar explorers. They were designed for a 5-year mission: Jupiter, Saturn, a handful of moons, then silence. That was the plan. Nearly 50 years later, they're still out there, still transmitting, still measuring, still sending back data from farther than any human-made object has ever traveled. And they're doing it with technology built before personal computers even existed. Each spacecraft runs on radioisotope thermoelectric generators, RTGs, powered by plutonium-238. The fuel decays naturally, producing heat, which is converted into electricity. At launch, each Voyager generated roughly 470 watts of power. Not much, about what a kitchen appliance uses, and that power has been declining ever since, dropping by about 4 watts every year. By 2026, Voyager 1 will have only around 250 watts remaining. That slow decline dictates everything. Every instrument, every heater, every transmission. When power drops, something has to be turned off. The cameras were shut down in 1990. Other instruments followed over the years, not because they failed, but because the spacecraft couldn't afford to keep them running. Voyager is not running out of capability. It's running out of electricity. Communication is even more remarkable. Voyager 1 is now so far away that its radio signal takes over 22 hours to reach Earth. Voyager 2 takes about 18. When engineers send a command, they wait nearly a full day just to know whether it arrived. Then they wait again for confirmation. A simple back-and-forth exchange takes almost 2 days. And the transmitter sending that signal? It outputs roughly 23 watts, less than a typical light bulb. By the time that signal crosses billions of miles of space and reaches Earth, it has weakened to a tiny fraction of a trillionth of a watt, one of the faintest signals humans routinely detect. Yet we decode it. But Voyager wasn't meant to go this far in the first place. Voyager didn't reach the edge of the solar system by accident. It got there because of timing. In the late 1970s, the outer planets aligned in a way that happens only once every 176 years. Jupiter, Saturn, Uranus, and Neptune positioned themselves so that a spacecraft could visit all four, using gravity alone to build speed. It was a rare cosmic shortcut. Without that alignment, exploring the outer giants would have required multiple missions and far more fuel than any rocket could carry. With it, One spacecraft could leap from planet to planet, gaining energy at each stop. This technique is called a gravity assist. The idea is simple. When a spacecraft swings past a massive planet, it doesn't just fall toward it and leave unchanged. It steals a tiny fraction of the planet's orbital momentum. The planet loses almost nothing. The spacecraft gains speed. Jupiter, the largest planet in the solar system, was the key. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed on September 5th, taking a faster trajectory. Despite launching second, Voyager 1 arrived at Jupiter first on March 5th, 1979, traveling about 17 kilometers per second, roughly 2 kilometers per second faster than its twin. That difference mattered. Jupiter didn't just provide photographs, it provided velocity. As Voyager swung around the gas giant, its path bent sharply. The planet's immense gravity redirected it toward Saturn, while increasing its speed relative to the Sun. Gravity didn't just guide Voyager, it accelerated its destiny. Saturn came next. Voyager 1 arrived in November 1980. Voyager 2 followed in August 1981. Again, gravity reshaped their trajectories. But this time, the missions began to diverge. Voyager 1's close flyby of Saturn's moon Titan tilted its trajectory upward, out of the plane of the solar system. That maneuver ended its planetary tour. From there, it was set on a direct path toward interstellar space. Voyager 2 took a different route. Instead of leaving the ecliptic plane, it used Saturn's gravity for another assist, one that sent it onward to Uranus and Neptune. In January 1986, Voyager 2 reached Uranus. It flew within about 81,500 kilometers of the cloud tops. No spacecraft had ever seen the planet up close before. No spacecraft has done so since. Then, in August 1989, Voyager 2 arrived at Neptune, the most distant planet in the solar system. It revealed violent winds exceeding 2,000 kilometers per hour and a dynamic atmosphere that few had expected. With Neptune, the grand tour was complete. 4 outer planets, dozens of moons, thousands of images. But the most important outcome wasn't just the data. It was the speed. Each gravity assist added energy. Each encounter pushed Voyager farther and faster than its onboard fuel ever could have. The spacecraft, designed for 5 years of exploration, had been flung onto escape trajectories. By the late 1980s, both Voyagers were traveling fast enough to leave the Sun's gravitational dominance entirely. They weren't just drifting outward. They were escaping. And that's when NASA made a decision that changed everything. Instead of shutting the mission down after Saturn, instead of letting the probes fade quietly into the dark, engineers and scientists extended the mission. It was renamed the Voyager Interstellar mission. The goal was no longer just planetary science. The goal was to explore the outer limits of the Sun's influence, the termination shock, the heliosheath, and eventually the heliopause. And every kilometer it traveled beyond Neptune brought it closer to a boundary scientists believed they understood. A boundary predicted to lie somewhere around 90 to 100 astronomical units. By early 1990, Voyager 1 had finished its encounters with Jupiter and Saturn. It was moving outward, climbing above the plane of the solar system, leaving the bright worlds behind. Then NASA made one final request. On February 14, 1990, engineers sent a command across billions of kilometers of space. Hours later, Voyager slowly turned its camera back toward the inner solar system. From a distance of about 6 billion kilometers, it began taking a set of images that would later be called the Solar System Family Portrait. Mercury was too close to the Sun to see clearly. Mars appeared as a faint point. Jupiter and Saturn were distant specks. And Earth? Earth appeared as a single pale pixel suspended in a narrow beam of scattered sunlight, less than 1 pixel wide. That tiny point became known as the pale blue dot. Everything we know exists inside that dot. Every ocean, every mountain, every city. From Voyager's distance, the entire human world had become a fraction of a pixel. The streak of light crossing the image was not cosmic dust or a distant nebula. It was sunlight scattered inside Voyager's camera lens. Even our view of Earth was partly an artifact of the instrument itself. The image marked a turning point for the mission. Up to that moment, Voyager had been photographing planets, moons, and rings. After this, it would never take another picture. Soon after the family portrait was completed, Voyager's cameras were powered down permanently. The reason was simple: energy. Every watt on the spacecraft had become precious. The cameras were among the most power-hungry instruments on board. To keep the scientific instruments running for as long as possible, the imaging system had to go dark. Voyager would never photograph another world again. It would never see a planet again. From that moment forward, the spacecraft would explore the solar system in a different way. Not with images, but with measurements. Magnetic fields, charged particles, plasma waves, invisible structures shaping the outer boundary of the sun's influence. The pale blue dot was not the edge of the solar system. It was simply the last time Voyager looked back. From there, it continued outward, beyond Neptune, beyond the Kuiper Belt, and toward a region no spacecraft had ever explored directly. The photographs were over. The real boundary still lay ahead. After that final glance, Voyager never looked back again. Long before Voyager ever approached the edge of the solar system, scientists believed they already understood what that edge should look like. Not because anyone had seen it, but because the physics seemed clear. The story begins with the Sun. The Sun is not a quiet star. Its outer atmosphere, the corona, reaches temperatures of over 1 million degrees Celsius. Gas that hot cannot remain bound forever. In the late 1950s, a young physicist named Eugene Parker proposed something radical. He argued that the Sun's atmosphere must constantly escape into space, not occasionally, continuously, a wind from a star. At first, the idea was controversial. Some scientists believed such a flow could only occur during solar storms. But in the early 1960s, spacecraft measurements confirmed Parker's prediction. The Sun was constantly blowing a stream of charged particles into space. Today we call it the solar wind. Near Earth, this solar wind typically moves at speeds of around 400 kilometers per second. Sometimes slower, sometimes faster. It is not a gas in the ordinary sense. It is a plasma, a mixture of protons and electrons so energetic that atoms cannot remain intact. Every second, the Sun loses roughly 1 million tons of material through this wind. That sounds enormous. But the Sun is so massive that at this rate, it would take trillions of years to lose a significant fraction of its mass. For billions of kilometers, this wind expands freely outward. But eventually, it must encounter resistance. The galaxy is not empty. Between the stars lies the interstellar medium, a thin mixture of gas, plasma, and magnetic fields. The density is extremely small. On average, it contains only about 0.1 atoms per cubic centimeter. For comparison, the air you are breathing right now contains roughly 10 to the power of 19 atoms per cubic centimeter. Interstellar space is therefore about 10 to the power of 19 times less dense than Earth's atmosphere. It is a vacuum better than anything we have ever encountered. But it is not nothing. Across cosmic distances, even this faint material exerts pressure. And the solar system is not stationary inside it. Our entire system is moving through the galaxy as it orbits the Milky Way's center, traveling at roughly 220 kilometers per second. From the sun's perspective, the interstellar medium behaves like a slow but persistent headwind. Where that headwind meets the outward pressure of the solar wind, a boundary must form. Scientists call the vast region created by this interaction the heliosphere. You can think of it as a giant bubble inflated by the sun. Inside the heliosphere, space is dominated by solar material and the sun's magnetic field. Outside it, the environment belongs to the galaxy. By the 1970s and 1980s, scientists had developed increasingly sophisticated models of this structure, using equations from magnetohydrodynamics, the physics describing electrically charged fluids interacting with magnetic fields. They simulated how the solar wind should behave as it pushes against interstellar space. The models produced a consistent picture. As the solar wind flows outward, it eventually slows when it encounters the pressure of the interstellar medium. The first major boundary should be the termination shock. Upstream of that shock, the solar wind moves faster than the speed at which pressure waves travel through the plasma. In other words, it is supersonic. When a supersonic flow meets resistance, a shock forms. At the termination shock, the solar wind should suddenly slow down. The plasma would compress. Temperatures would rise. Energetic particles would be accelerated by the turbulent magnetic fields surrounding the shock. Beyond that region lies the heliosheath. This is a turbulent zone where the slowed solar wind is diverted sideways as it tries to flow around the obstacle created by the interstellar medium. The plasma here should still originate from the sun, but it would be hotter, denser, and chaotic. Finally, at the outermost boundary, the solar wind would stop entirely. This boundary is called the heliopause. It marks the point where the outward pressure from the sun balances the inward pressure of interstellar space. Inside the heliopause, the sun still dominates the environment. Outside it, the galaxy does. By the late 20th century, models predicted the heliopause should lie roughly around 90 to 100 astronomical units from the sun. One astronomical unit is the distance between Earth and the sun, about 150 million kilometers. So that prediction placed the edge of the sun's influence somewhere between 13 and 15 billion kilometers away, and scientists believed the crossing would be unmistakable. 3 signals should appear almost simultaneously. First, the solar wind particles should collapse to extremely low levels. Those particles originate from the sun, so once a spacecraft enters interstellar space, they should largely disappear. Second, galactic cosmic rays should increase sharply. These are high-energy particles produced by violent events across the galaxy. Supernova explosions and other energetic processes. Inside the heliosphere, the sun's magnetic field helps shield the solar system from many of them. Outside the heliopause, that shielding weakens, one signal falling, another rising. But the clearest indicator was expected to be the magnetic field. Inside the heliosphere, the sun's magnetic field is carried outward by the solar wind. Because the sun rotates, These magnetic field lines twist into a spiral structure known as the Parker spiral. The galaxy's magnetic field, however, points in a different direction. So when Voyager crossed the heliopause, the orientation of the magnetic field around the spacecraft should rotate noticeably. Solar wind collapsing, cosmic rays increasing, magnetic field turning, three signatures marking the boundary. By the early 2000s, scientists were confident in this picture. The equations were well understood. The models had been refined for decades. The physics appeared consistent. They might have been uncertain about the exact distance. But the structure itself seemed clear. Voyager was approaching a boundary that theory had already mapped. And when the spacecraft finally reached it, scientists expected the data to confirm what the models predicted. But when Voyager approached that boundary, nothing behaved exactly the way it was supposed to. For years, Voyager 1 had been moving steadily outward, past Saturn, past Neptune's orbit, deep into the outer regions of the Sun's influence. And then, in December 2004, something finally changed. At a distance of about 94 astronomical units from the Sun, Voyager's instruments detected a sudden shift in the particle environment around the spacecraft. The solar wind slowed sharply. Plasma density increased. Energetic particles surged. Voyager had reached the termination shock. This was the first major boundary predicted by heliosphere models. The place where the solar wind, which had been expanding freely for billions of kilometers, finally began to slow under pressure from interstellar space. At first, the numbers looked reassuring. Voyager encountered the shock at 94 astronomical units. The models had predicted roughly 90 to 100 astronomical units, close enough to feel like confirmation. For scientists who had spent decades refining these models, it was an encouraging moment. The spacecraft had reached exactly the kind of boundary theory said should exist. But then something strange began to appear in the data. Voyager didn't just cross the shock once. Over the following months, the spacecraft appeared to encounter it multiple times. One moment, the instruments showed conditions expected beyond the shock: slower solar wind and turbulent plasma. Later, the signatures of the shock would appear again. It was as if the boundary itself was moving. At first, this seemed puzzling. A structure spanning billions of kilometers should not shift back and forth over a spacecraft traveling thousands of kilometers every hour. But the explanation turned out to lie much closer to home. The Sun. The Sun does not produce a constant solar wind. Its activity rises and falls in an approximately 11-year solar cycle. During more active periods, the solar wind becomes stronger, pushing the outer boundaries of the heliosphere farther outward. During quieter periods, the pressure weakens, allowing interstellar space to push inward. In effect, the entire heliosphere expands and contracts. The termination shock wasn't a rigid wall. It was a moving surface. The boundary wasn't fixed. It was breathing. That realization didn't overturn the existing models, but it added complexity. The outer edge of the Sun's influence was not static. It responded to changes in solar activity across the entire solar system. Still, at this point, the overall picture remained intact. The termination shock existed. Voyager had reached it roughly where expected, and the heliosphere still appeared to behave broadly the way theory predicted. Then, a second spacecraft arrived. In August 2007, Voyager 2 encountered the termination shock as well. But this time, the distance was different. Voyager 2 crossed the shock at about 84 astronomical units from the Sun. nearly 10 astronomical units closer than Voyager 1. 10 astronomical units is not a small difference. 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. A 10 AU difference means the boundary appeared 1.5 billion kilometers closer in Voyager 2's direction. At first, scientists wondered if solar activity might explain the discrepancy. The Sun's cycle could shift the boundary inward or outward slightly. But the difference seemed too large for that alone. Gradually, a new picture began to emerge. The heliosphere was not perfectly round. Instead of a neat, spherical bubble surrounding the Sun, the structure appeared distorted, compressed in some directions and stretched in others. One reason was the Sun's motion through the galaxy. As the solar system moves through the interstellar medium, that motion creates something like a headwind. The heliosphere is pushed backward, forming a shape that may resemble a bullet or a teardrop, with a rounded front and an extended tail trailing behind. In such a structure, the termination shock would not occur at the same distance in every direction. In some regions, it would be farther away. In others, closer. Voyager 1 and Voyager 2 were sampling different parts of that structure. For scientists, this was surprising, but still manageable. The heliosphere was more complex than the early model suggested, but the basic framework still seemed valid. The Sun inflated a vast bubble in space. That bubble had layers, and the spacecraft were gradually moving toward its outer edge. At this stage, the deviations looked like refinements, not contradictions. The models still appeared broadly correct. But the outer solar system had already shown a pattern. At Jupiter, expectations had been wrong. At Saturn, new complexities appeared. At Uranus and Neptune, the structure of the system proved stranger than predicted. And now, even the boundary of the heliosphere was beginning to behave in unexpected ways. Still, none of this prepared scientists for what Voyager would measure next. After crossing the termination shock, Voyager 1 continued moving outward through the Helios sheath. Scientists expected the next boundary, the heliopause, to appear within a few years. And when it did, the crossing should be obvious. Solar wind particles would collapse. Galactic cosmic rays would surge. The magnetic field would rotate to match the direction of the galaxy. 3 signals: clear, sudden, unmistakable. But the data Voyager sent back did not behave that way. Around 2009 and 2010, the particle instruments began detecting something unusual. The number of galactic cosmic rays was slowly rising. These particles originate from outside the solar system, from supernova explosions and other energetic events across the Milky Way. Inside the heliosphere, the Sun's magnetic field blocks many of them. So as Voyager moved outward, scientists expected their numbers to increase. But not yet. The spacecraft should still have been deep inside the heliosphere. And yet the increase had already begun. At the same time, particles from the Sun, carried outward by the solar wind, were beginning to decline. It was the pattern expected near the heliopause, but it was happening gradually, not over weeks, over months, and then years. Voyager seemed to be approaching the edge of the solar system, but never quite reaching it. Then another signal appeared. Voyager's instruments began detecting streams of charged particles traveling along magnetic field lines in an unexpected way. Instead of being trapped neatly inside the heliosphere, some particles were moving freely along extended magnetic pathways. Galactic particles appeared to be entering along these routes, while solar particles escaped outward along the same channels. Researchers began calling these structures magnetic highways. Along these pathways, charged particles could travel enormous distances with very little scattering. It was as if invisible corridors had formed near the outer edge of the heliosphere. The boundary was not behaving like a solid barrier. Instead of a clean separation between two environments, Voyager appeared to be drifting through a region where solar and interstellar particles could mix along magnetic field lines. For some scientists, this suggested that the heliopause might be far more complicated than models predicted. Perhaps the boundary was not a sharp surface at all. Perhaps it was layered. But there was still one problem. The magnetic field direction had not changed. Inside the heliosphere, the sun's magnetic field follows the Parker spiral pattern created by the sun's rotation. Outside the heliosphere, the galaxy's magnetic field should point in a different direction. If Voyager had crossed the heliopause, the orientation of the field should have rotated. But it didn't. The magnetic field remained aligned with the sun. That detail kept the debate alive. By 2011 and early 2012, Voyager's instruments were reporting particle levels never measured before at that distance. Galactic cosmic rays were approaching intensities expected in interstellar space. Meanwhile, solar particles had dropped to extremely low levels. Two of the expected signals were already appearing, but the third, the magnetic field rotation, was missing. Some researchers began cautiously suggesting that Voyager might already be outside the heliosphere. Others strongly disagreed. Without the magnetic field changing direction, they argued, the spacecraft must still be inside the sun's domain. The evidence pointed both ways. Voyager was clearly approaching something, but exactly what it was approaching remained uncertain. The spacecraft continued moving outward at about 17 kilometers per second, covering nearly 6 astronomical units each year. Month by month, the data continued to evolve. And then, in the summer of 2012, everything changed. Within a single week, the particle environment around Voyager shifted more dramatically than at any point in the previous decade. Signals that had been drifting slowly for years suddenly jumped. And the data from that week would force scientists to reconsider what the edge of the solar system really looks like. Then came a week that changed everything. For years, Voyager 1 had been drifting through a region that refused to behave the way scientists expected. Particle levels were changing slowly. Magnetic structures were behaving strangely. And the spacecraft seemed to hover near the boundary between two environments. Then, everything shifted. On August 25, 2012, Voyager's instruments recorded a sudden and dramatic change in the particle environment around the spacecraft. The shift did not unfold over months. It happened within days. First, the particles coming from the sun collapsed. These particles, carried outward by the solar wind, had surrounded Voyager for the entire mission. They originated from the sun and dominated the heliosphere. Suddenly, their intensity dropped sharply, almost to zero. At nearly the same time, another signal surged. The detectors measuring galactic cosmic rays recorded a rapid increase in high-energy particles arriving from outside the solar system. These particles had been gradually rising for years, but now their intensity jumped to levels never before measured by a spacecraft so close to the sun. One signal falling, another rising. Exactly the pattern scientists expected if Voyager had crossed the heliopause. But there was more. Voyager carried an instrument capable of detecting plasma waves in the surrounding environment. By analyzing these waves, scientists could estimate the density of the plasma around the spacecraft. Shortly after the particle transition, the data revealed something remarkable. The plasma density had increased dramatically. Inside the heliosphere, plasma densities are relatively low because the solar wind spreads outward over enormous distances. But in the interstellar medium, the density is slightly higher. Voyager's measurements indicated a density consistent with interstellar plasma. The spacecraft appeared to have entered interstellar space. For the first time in human history, a machine built by our species had reached the environment between the stars. But one critical signal was still missing. The magnetic field had not rotated. According to decades of models, the heliopause should separate the sun's magnetic field from the galaxy's magnetic field. Crossing that boundary should cause a noticeable change in the direction of the field lines surrounding the spacecraft. Yet Voyager's magnetometer showed something unexpected. The direction of the magnetic field remained almost perfectly aligned with the field it had measured inside the heliosphere. The spacecraft appeared to be outside the sun's particle environment, but still connected to the sun's magnetic field. This contradiction puzzled scientists. Had Voyager really crossed the heliopause? Or had it entered some new type of transitional region no one had predicted? The data forced researchers to reconsider the nature of the boundary itself. Instead of a clean surface separating two magnetic domains, the heliopause appeared to be structured and layered. Magnetic field lines from the sun and the interstellar medium could reconnect and intertwine, allowing particles from both environments to mix. The edge of the heliosphere was not a simple dividing line. It was a complex interface. Because of this uncertainty, NASA did not immediately announce the discovery. Scientists spent months analyzing the measurements. They compared data from different instruments. They examined plasma wave signals and particle spectra. They debated whether the evidence truly indicated that Voyager had entered interstellar space. Only after careful review did the conclusion emerge. In September 2013, NASA publicly confirmed that Voyager 1 had crossed the heliopause. The spacecraft was now traveling through interstellar space, about 121 astronomical units from the Sun. But the story did not end there. For some scientists, the most surprising part was not that Voyager had crossed the boundary, it was how it had crossed it. The heliopause did not behave like the clean, spherical surface predicted by early models. Instead, the crossing occurred through a complex magnetic structure where particle populations changed dramatically, while the magnetic field direction remained similar. In other words, the spacecraft had entered interstellar space without the magnetic rotation scientists expected. The models had captured the broad structure of the heliosphere correctly, but the detailed physics of the boundary was more complicated than anyone had imagined. 6 years later, a second spacecraft provided confirmation. In November 2018, Voyager 2 also crossed the heliopause. Its instruments detected a similar pattern. Solar wind particles dropped sharply, galactic cosmic rays increased, and plasma density rose. Two spacecraft, separated by billions of kilometers, had now sampled the same boundary. The Sun's influence ended somewhere beyond 120 astronomical units. And beyond that distance lay the true environment of the galaxy. For the first time in human history, we were touching another star's environment. But crossing the boundary was not the end of Voyager's discoveries. It was only the beginning of what the spacecraft would reveal about the vast region beyond our solar system. When Voyager 1 crossed the heliopause in 2012, the event answered one question, but it raised several new ones. For decades, scientists had imagined the edge of the solar system as a relatively simple boundary, a place where the sun's influence ended and interstellar space began. Voyager showed something more complicated. Instead of confirming the model exactly as expected, the spacecraft revealed that the heliosphere behaves more like a dynamic frontier than a clean dividing line. Over time, the data from Voyager 1 and Voyager 2 began to reshape that picture. Taken together, their measurements revealed 7 key discoveries that changed how scientists understand the outer boundary of the solar system. Group A, the structure of the boundary. The first set of discoveries involved the shape and location of the heliosphere itself. First, the boundary was farther away than many early estimates suggested. Voyager 1 crossed the heliopause at roughly 121 astronomical units from the Sun. Voyager 2 crossed at about 119 astronomical units in 2018. Earlier models had predicted the heliopause closer to 90 to 100 astronomical units. The basic structure was correct, but the scale was larger. Second, the heliosphere is not symmetrical. The difference between Voyager 1 and Voyager 2 crossings confirmed that the heliosphere is compressed in some directions and stretched in others. The Sun is moving through the interstellar medium, and that motion creates pressure that distorts the heliosphere's shape. Instead of a neat, spherical bubble, the heliosphere appears more like a teardrop or bullet-shaped structure moving through space. Third, the boundary itself is not a thin surface. Early models imagined the heliopause as a relatively sharp transition. Voyager showed that the region near the boundary is layered and structured, with complex magnetic interactions and particle exchange occurring across multiple regions. In other words, the edge of the solar system behaves more like a coastline than a wall. Group B, dynamic processes. Voyager also revealed that the outer heliosphere is far more dynamic than scientists once believed. Fourth, the spacecraft detected what researchers began calling magnetic highways. Along certain magnetic field lines near the heliopause, charged particles could travel long distances with relatively little scattering. These pathways allowed galactic cosmic rays to enter the heliosphere, while solar particles escaped outward along the same routes. Instead of a sealed magnetic barrier, the boundary behaves like a network of connected magnetic channels. Fifth, Voyager observed enormous disturbances propagating through the helios sheath. These disturbances were triggered by powerful solar storms originating near the Sun. When large eruptions of solar plasma traveled outward through the heliosphere, they created pressure waves that moved through the outer boundary region. Some researchers compared these events to tsunami-like waves in space, compressing plasma and temporarily altering particle densities even billions of kilometers from the Sun. The heliosphere was not simply expanding outward, it was constantly responding to activity at its center. Group C, radiation environment. The final set of discoveries involved the radiation environment surrounding the solar system. Sixth, Voyager's measurements revealed new details about cosmic ray behavior near the heliopause. The spacecraft detected subtle directional patterns in the incoming cosmic rays, a phenomenon known as anisotropy. These patterns suggested that cosmic rays were not entering the heliosphere evenly from all directions, but instead were guided along magnetic structures near the boundary. The heliopause acted not only as a shield, but also as a complex filter shaping how cosmic radiation enters the solar system. Seventh, Voyager measured properties of the local interstellar medium directly for the first time. The plasma density outside the heliopause turned out to be slightly higher than many earlier estimates suggested. While still extremely sparse, far thinner than any atmosphere. The environment between the stars was not completely uniform. Small variations in density and magnetic field structure appear to influence how the heliosphere interacts with the galaxy around it. Taken together, these discoveries reshaped the scientific picture of the solar system's frontier. The heliosphere is larger than expected. Its shape is asymmetric. Its boundary is layered and dynamic. Particles move along magnetic corridors. Solar storms send waves through the outer regions. And interstellar space itself is more structured than once believed. Reality was more complex than the model, and far more interesting. Voyager did not simply confirm what scientists already knew. It revealed that the boundary between our star and the galaxy behaves like a living system, shaped by motion, magnetism, and plasma flows operating across enormous distances. We once imagined the edge of the solar system as a line. Instead, Voyager showed that we were drifting along a dynamic shoreline between two environments. And even now, decades after its launch, the spacecraft continues moving outward through that frontier, still measuring, still sending data, still expanding our understanding of where the sun's influence ends and interstellar space begins. And yet, even now, Voyager's story is not over. Voyager 1 is now the most distant human-made object ever launched, more than 24 billion kilometers from Earth, over 160 astronomical units from the Sun, and still moving outward at about 17 kilometers per second. Every year, it travels roughly 6 astronomical units farther into interstellar space, a distance greater than the orbit of Mars. But while the spacecraft continues its journey, something else is happening quietly on board. Voyager is slowly running out of power. The spacecraft generates electricity using radioactive fuel that has been producing energy since launch in 1977. That energy source has been remarkably reliable, but it fades a little each year. Roughly 4 watts of power disappear annually. That gradual loss forces engineers to make difficult choices. Over the decades, instruments have been turned off one by one to keep the most important systems alive. The cameras were the first to go silent long ago. Then several scientific instruments followed. Today, only a small number of sensors remain active, just enough to continue studying the environment beyond the heliosphere. Each shutdown buys the spacecraft a little more time, but the margin grows thinner every year. Communication itself has also become a test of patience. At Voyager's current distance, a radio command sent from Earth takes about 22 hours to reach the spacecraft. A response takes another 22 hours to travel back. Even the simplest adjustment becomes a conversation lasting nearly 2 days. Engineers must plan every command carefully, knowing that mistakes cannot be corrected quickly. And yet the spacecraft still responds. Even after nearly half a century in space, in recent years, Voyager's engineering team faced a reminder of how fragile that connection has become. At one point, the spacecraft began transmitting strange telemetry data from its attitude control system, the system responsible for keeping Voyager's antenna pointed toward Earth. The spacecraft itself appeared to be operating normally. But the engineering data describing its orientation suddenly stopped making sense. Some numbers were clearly incorrect. Diagnosing the problem was not easy. The spacecraft was billions of kilometers away, running on technology designed in the 1970s. There was no way to physically inspect the system. Engineers had only the faint radio signal and decades-old documentation to work with. After careful investigation, the team traced the problem to corrupted data being sent from one section of the spacecraft's computer memory. To correct it, they prepared a remote software adjustment essentially rewriting a small part of Voyager's code from across the solar system. The command was transmitted. Then they waited. Nearly a full day passed before Voyager received the instructions. Another day passed before the spacecraft's reply reached Earth. Slowly, the data stabilized. The system recovered. The spacecraft continued operating. It was a small victory, but an extraordinary one. A machine launched before many of today's engineers were born had responded to commands sent across billions of kilometers of space. Voyager was still listening, still answering, still working. But the reality remains unavoidable. The spacecraft is aging. Temperatures inside some systems are slowly dropping as electrical power declines. Every year, another decision must be made about which instruments can remain active. NASA's engineers extend the mission 1 year at a time, as long as power remains, as long as the antenna stays aligned, as long as the signal continues arriving. Meanwhile, Voyager continues drifting outward. The spacecraft has already passed the heliopause, the boundary where the sun's particle environment gives way to interstellar space. But the solar system's gravitational influence stretches far beyond that region. Far beyond the planets lies the distant Oort cloud, a vast halo of icy objects that may extend tens of thousands of astronomical units from the sun. Voyager is still deep within that enormous cosmic neighborhood. Yet the spacecraft's voice grows quieter with each passing year. One day, the available power will fall below the level needed to operate its transmitters. The instruments will shut down. The antenna will stop sending data, and the faint signal that has traveled across billions of kilometers will simply fade into silence. When that happens, Voyager's long conversation with Earth will end, but the spacecraft itself will continue moving, long after the last signal disappears, drifting silently through the galaxy, carrying with it a small golden record, a message from one tiny world orbiting an ordinary star. And long after that signal goes silent, Voyager will still be moving. The moment the final signal from Voyager fades into space will be a bittersweet milestone for humanity. But for the universe, it will be little more than a blink of an eye. When the spacecraft's voice finally falls silent, a new reality will emerge. The true journey of Voyager will only just be beginning. There is a common misconception that crossing the heliosphere means leaving the solar system. In reality, it is not that simple. The universe operates on scales that are almost impossible to imagine. Although Voyager 1 has entered interstellar space, it has not truly escaped our cosmic neighborhood. Ahead of the spacecraft lies the Oort cloud, a vast spherical shell containing trillions of icy objects, remnants from the earliest formation of the solar system. To understand the scale of this region, consider this. Voyager will need roughly 300 more years just to reach the inner edge of the Oort cloud. To travel completely across that immense structure will require another 30,000 years. Only after passing beyond the far side of the Oort cloud, where the sun's gravitational influence finally fades, will Voyager truly leave the solar system and become a traveler of the galaxy. During all that time, and for tens of thousands of years beyond, Voyager will likely collide with nothing at all. Space is astonishingly empty. Voyager 1 is currently heading toward the direction of the constellation Ophiuchus. In about 40,000 years, it will pass near the star Gliese 445, coming within roughly 1.6 light-years of it. It will not stop there. It will not orbit. It will simply drift past, like a silent mechanical ghost moving through the darkness. even after its power fades and it can no longer transmit data. Voyager still carries something extraordinary with it. The golden record. This is not merely a gold-plated metal disc. It is humanity's attempt to summarize its own existence and send that message into the far future. Engraved onto that record are 116 images of Earth, ranging from the structure of DNA and the planets of our solar system to scenes of everyday human life. People eating, working, and building civilizations. The sounds of Earth. Waves breaking on a shore, thunder rolling across the sky, wind moving through the air, birds singing, and even the cry of a newborn child. Greetings spoken in 55 languages, including several ancient languages that have already disappeared from everyday use. A collection of music drawn from many cultures, from the compositions of Bach and Beethoven to traditional songs from different parts of the world. On the outside of the record's protective cover, engineers engraved instructions explaining how it could be played. Those instructions are written not in any human language, but in the universal language of mathematics and physics. But we should be honest. The probability that an extraterrestrial civilization will ever discover Voyager is extremely small. The scientists who designed the record understood that when they launched it. So what is the true purpose of the golden record? It is not a letter expecting a reply. It is a declaration of existence. It is a time capsule of humanity. Like a message sealed in a bottle and cast into the cosmic ocean, its purpose is simply to say, at some moment in time, in a small corner of space, we were here. We lived, we loved, we created, and we wondered about the universe beyond our world. When you look up at the night sky, remember that somewhere out there, a small machine is carrying our laughter and our music into the darkness. It is moving alone, deeper into interstellar space. It does not feel fear, because it cannot feel anything at all. It simply continues doing what we taught it to do. Keep going. Thank you for staying with us until this moment. If you're listening at the end of a long day, allow yourself to let go of whatever has been weighing on your mind. Settle into a comfortable place. Breathe slowly. Let your thoughts drift as the universe continues its quiet motion. There's nothing you need to do right now. Nothing you need to solve. If you'd like, feel free to share your thoughts with us in the comments. We always enjoy hearing from you. Until next time, rest well and sleep peacefully.